Imagine that everything you see in the universe, from galaxies and stars to the planet Earth itself, started from an infinitely small and hot point. Yet, a terrifying theory suggests that everything we know might have come into existence from nothing. Another theory posits that the universe originated from a single point, with a massive explosion known as the Big Bang, creating all matter and energy. The Big Bang theory is one of the primary explanations for the origin of the universe, but it has its flaws. For example, the Big Bang cannot fully explain what existed before the explosion or phenomena like cosmic inflation that remain poorly understood. Theories such as parallel universes and eternal inflation suggest that understanding these concepts could change our simple view of a complex universe. Overall, gaining knowledge on this topic helps us predict the future of our universe. In this video, we delve into how the universe came into existence. From ancient times to the present day, there have been many different opinions, some illogical and some widely accepted. To better understand this topic, we will explore ancient theories and later scientific theories, analyzing evidence and clues, and examining related concepts like parallel universes. However, this is not enough. Questions remain, such as, what existed before the explosion? Did the universe really begin from nothing? How did an explosion occur in a vacuum? How did an explosion happen without a cause? What is the fate of the universe? Stay with us until the end as we address these questions. Ancient theories about the origin of the universe were a mix of mythology, religion, and philosophy, all attempting to explain the great mysteries of the cosmos. In ancient civilizations, myths and creation stories played a crucial role in people's worldview. For example, in Egyptian mythology, the sun god was regarded as the primary creator who brought the world into existence from chaotic waters. Similarly, in Mesopotamian mythology, the world was created from the battle between gods, such as the Battle of Marduk with the sea dragon Tiamat. These myths and stories not only provided explanations for the origin of the universe, but also reflected the values and beliefs of those cultures. Interestingly, some of these myths have surprisingly scientific origins, though most are scientifically disproven. On the other hand, ancient philosophers had their own theories about the origin of the universe based on observation and logical thinking. One such philosopher was Anaximander, a pre-Socratic Greek philosopher who proposed fascinating theories about the cosmos's origin. He believed that the universe originated from an indefinite and boundless substance called apeiron. This primal substance gradually differentiated into various components of the cosmos. Anaximander believed that natural laws governed everything, and the universe emerged based on logical order rather than divine intervention. His theories were somewhat scientific and can be seen as precursors to modern theories. The Big Bang theory is one of the central theories in modern cosmology, proposing that the universe began with a massive and sudden explosion approximately 13.8 billion years ago. This explosion, known as the Big Bang, started from an infinitely small and dense point and expanded rapidly in an instant. Key evidence supporting this theory includes the cosmic expansion discovered by Edwin Hubble in the 1920s and the cosmic microwave background, Cetus EMB radiation, which represents the residual heat from the Big Bang. While widely accepted in the scientific community, many questions still remain. One of the major challenges of the Big Bang theory is its connection to the concept of a universe starting from nothing. According to the principles of quantum physics, even in a complete vacuum, energy and virtual particles can spontaneously create and quantum fluctuations can occur. These fluctuations could lead to the creation of the universe, a theory some scientists use to explain the universe's origin. Therefore, the Big Bang theory and the theory of the universe starting from nothing can complement each other. The Big Bang refers to the expansion and evolution of the universe following its initial creation, while quantum fluctuations explain how this initial creation might have occurred. New scientific theories have also delved into more complexities in understanding the origin of the universe. One such theory is the eternal inflation theory, which proposes that cosmic inflation not only occurred at the beginning of the universe, but also continues endlessly in different parts of space. This theory explains why the universe appears homogeneous and isotropic, meaning on large scales, the universe looks the same in every direction, with no observed differences in structure. In other words, cosmic inflation caused various regions of space to expand at incredibly fast rates, leading to the current state. This theory also suggests that new universes are formed in different parts of space, known as the multiverse theory. According to this theory, there may be thousands of parallel universes, each with its own unique physical properties and laws. It's even possible that other versions of ourselves exist in these parallel universes, living under different conditions. It's quite fascinating. Now let's dive deeper into this theory. Theories related to the creation of the universe are very diverse, each explaining different aspects of this complex process. Some of these theories involve the concepts of dark matter and dark energy, which are respectively responsible for the formation of large cosmic structures and the accelerated expansion of the universe. These unknown forces are still the subject of extensive research and could provide us with a better understanding of the universe's evolution and its ultimate fate. Now, let's examine the role of these concepts which constitute the majority of the universe. Dark matter is one of the great enigmas of cosmology. This invisible matter, detectable through its gravitational effects on celestial bodies and light, plays a crucial role in the formation of galaxies and galaxy clusters. Without dark matter, galaxies could not rotate at their current speeds and would likely disintegrate easily, as dark matter provides the necessary gravitational force for stability. Dark energy. Now let's move on to dark energy, which makes up a larger portion of the universe. Dark energy is another mysterious component of the universe. As previously mentioned, this energy constitutes most of the universe and is responsible for the accelerated expansion of the cosmos following the Big Bang. Dark energy causes the distances between galaxies to increase over time, leading to a future state where galaxies may move out of each other's observable range. Gravity not only keeps us anchored to Earth, but is also a key to understanding the formation and evolution of the universe. Einstein's general theory of relativity shows that gravity is caused by the curvature of space and time, by mass and energy. This theory is confirmed not only on a cosmic scale, but also in planetary orbits and even in laboratory experiments. One of the significant pieces of evidence for gravity is the bending of starlight by massive objects, a phenomenon known as gravitational lensing. Dark matter, which constitutes 27% of the universe's total mass energy, plays a crucial role in the formation of galactic structures. Although we cannot directly observe dark matter, its gravitational effects on the motion of stars and galaxies indicate its presence. As we mentioned, without dark matter, galaxies would not be stable. The cosmic microwave background, CMB, is radiation that has reached us from the early moments after the Big Bang and provides valuable information about the universe's initial composition and temperature. The CMB indicates the uniform distribution of matter and energy in the universe's early moments and helps us develop more precise cosmological models. Studying this radiation allows scientists to test theories related to the universe's initial expansion and the properties of dark matter and dark energy. Quantum fluctuations played a key role in the distribution of matter and energy in the very early moments of the universe. These fluctuations led to small density variations that gradually led to the formation of galaxies and larger structures. Through the theory of cosmic inflation, we can explain these fluctuations and gain a better understanding of the universe's initial evolution. As we previously discussed, let's delve deeper into this fascinating topic. Don't forget to like the video before we continue. The multiverse hypothesis suggests that other universes may exist, each formed with different physical laws and initial conditions. The idea of bubble universes is similar, imagining universes each existing in separate bubbles that may never interact with each other. While you might be familiar with these concepts, let's explore the various theories, types of multiverse theories. 1. Inflationary multiverse. Theory. This theory is based on cosmic inflation and suggests that different regions of space-time can independently inflate, creating new universes. These universes might have different physical laws and properties. In some interpretations, there may be other versions of us living in different conditions in these universes. 2. Quantum multiverse theory. Based on the many worlds interpretation of quantum mechanics, Everett's interpretation, every decision and event can lead to the branching of a new universe. Therefore, there could be infinitely many parallel universes, each with different versions of ourselves, making different decisions and leading different lives. 3. String theory. Multiverse. String theory also suggests the existence of parallel universes where additional dimensions and different physical laws might exist. These universes may not directly correlate with other versions of us, but represent fundamentally different worlds. The question of what existed before the beginning of the universe is one of the most complex and debated questions in cosmology. Some theories suggest that different states of energy or even parallel universes existed before the Big Bang. The Clash of Brains theory proposes that the Big Bang might have been the result of the collision of two brains or parallel universes. Although these theories still require more evidence, they offer new and exciting perspectives for understanding the origin and evolution of the universe. One of the most fundamental questions in cosmology is whether the universe will continue to expand forever or eventually contract again. Since the Big Bang, the universe has been expanding, and this expansion is accelerating, likely due to the influence of dark energy. Different models for the future of the universe exist, depending on the amount of dark energy and how it changes over time. If dark energy remains constant, the universe will likely continue to expand eternally. However, if its amount decreases, the universe may ultimately contract, leading to a scenario known as the Big Crunch. The universe has undergone various stages since the Big Bang. After a period of cosmic inflation that homogenized the distribution of matter and energy, the universe entered a phase of slower expansion and the formation of the first elementary particles and atoms. Subsequently, galaxies, stars, and planets formed. In the future, the universe may continue to cool and energy sources may erode, ultimately leading to the heat death of the universe. In this state, all energy sources are evenly distributed and no active cosmic processes remain. One hypothesis about the universe's future is the Big Freeze, where the expansion continues, leading to extremely low temperatures throughout the cosmos. Conversely, the Big Crunch hypothesis suggests that if dark energy dissipates, gravitational forces could overcome the expansion, causing the universe to contract. This contraction could result in the universe's complete collapse. Another theory to consider is the Big Rip, where dark energy becomes so strong that it not only tears galaxies apart, but even disintegrates atoms and fundamental particles. One of the exciting new developments in cosmology is the discovery of extremely distant galaxies using the James Webb Space Telescope. This telescope, with its high-resolution capabilities and infrared detection, allows scientists to peer deep into the cosmos and observe regions that formed close to the time of the Big Bang. One such discovery is the observation of the galaxy GNZ 11, approximately 13.4 billion light-years away, making it one of the oldest known galaxies. These observations provide valuable information about the formation and evolution of the first galaxies and stars, helping us develop new theories about the early stages of the universe's evolution post-Big Bang. Additionally, new observations of gravitational waves enable scientists to study collisions of black holes and neutron stars, furthering our understanding of extreme physics and its impact on the cosmos. To better understand this topic, let's examine some key concepts separately, and then we'll address the questions. One of the most astonishing phenomena in quantum physics is quantum entanglement. This phenomenon states that two particles can become entangled in such a way that the state of one instantly affects the state of the other, regardless of the distance between them. This connection between particles is so strange and beyond time that Albert Einstein called it spooky action at a distance. Quantum entanglement has numerous applications in advanced technologies such as quantum computing and secure quantum communications. Symmetry breaking and symmetric universe. Symmetry breaking is a fundamental concept in physics that explains how physical laws that were initially symmetrical can gradually become asymmetrical under certain conditions. This phenomenon occurred in the early moments of the universe after the Big Bang and played a crucial role in the formation of complex cosmic structures. For instance, symmetry breaking in fundamental forces led to small but critical differences between matter and antimatter, ultimately resulting in the formation of a matter-dominated universe. The four fundamental forces shaping our universe are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these forces plays a specific role in the structure and functioning of the cosmos. For example, gravity is primarily responsible for the formation and evolution of galaxies, stars, and planets, while the strong nuclear force holds atomic nuclei together. Understanding these forces and their interactions helps us explain complex phenomena such as supernova explosions and the formation of heavy elements. Thermal fluctuations in quantum physics refer to small and random changes in the energy and states of particles due to continuous fluctuations on very small scales. These fluctuations played a vital role in the distribution of matter and energy in the early moments after the Big Bang, and led to the formation of large structures such as galaxies. This phenomenon is particularly important in explaining the theory of cosmic inflation and the initial non-uniform distribution of matter and energy. The hypothetical inflaton field plays a crucial role in the theory of cosmic inflation, which explains how the universe rapidly expanded in the initial moments after the Big Bang. This hypothetical field can explain why the universe appears uniform and homogeneous, while large-scale inhomogeneities exist. The inflaton field provided the necessary energy for the rapid expansion of the cosmos, causing small quantum fluctuations to turn into significant density differences, ultimately leading to the formation of galaxies and cosmic structures. Finally, we have reached the section we've all been waiting for. Let's satisfy our curiosity, though human curiosity is more abundant than the number of galaxies. Let's dive into the first question. How did the explosion in a vacuum occur? The Big Bang, which marks the beginning of our universe, was not a conventional explosion, but rather a rapid and astonishing expansion from an extremely dense and hot state. This expansion did not occur in a vacuum. Instead, the vacuum and cosmic space resulted from this process. Before the Big Bang, all the matter and energy in the universe were concentrated in an infinitely small and dense point. As the expansion began, this matter and energy rapidly spread out, leading to the formation of galaxies, stars, and planets. This process is still ongoing, and the universe continues to expand. How did the explosion occur? Without a cause. One of the great mysteries of cosmology is how the Big Bang occurred without a specific cause. Some theories suggest that the Big Bang could be the result of quantum fluctuations in the vacuum. In quantum physics, the vacuum constantly experiences small and temporary fluctuations that can lead to more significant events. These fluctuations can randomly and spontaneously generate and result in an explosion similar to the Big Bang. However, this is only a hypothesis, and scientists are still working to find precise evidence and explanations for this phenomenon. What will be the future of the universe? As we mentioned, the future of the universe heavily depends on the behavior of dark energy. If dark energy remains the dominant force in the cosmos, the universe's expansion will continue to accelerate, leading to a state known as the Big Freeze, as we referenced earlier. In this scenario, galaxies will gradually move away from each other, and low temperatures will prevail throughout the cosmos. However, if dark energy diminishes or changes, gravitational forces may overcome the expansion, causing the universe to contract in a process known as the Big Crunch. Another theory, the Big Rip, suggests that dark energy could become so strong that it tears apart not only galaxies, but even atoms and fundamental particles. Although we discussed this topic in the previous section about cosmic developments, it was necessary to answer this question here. Evolution of future theories. Beyond the mentioned theories, scientists continue to explore other hypotheses. For example, the oscillating universe theory suggests that the universe may cyclically move between periods of expansion and contraction. In this theory, the current Big Bang is just one of endless cycles where the universe contracts to a dense state and then undergoes a new Big Bang, leading to expansion. These models and theories are continually updated based on scientific advancements and new observations. It's fascinating to think that we might just be one instance in the cycles of the universe's formation. In this video, we examined and discussed how the universe started. We analyzed clues that support this matter and reviewed ancient thoughts on this topic. Additionally, we discussed astonishing theories that might occur. For more exciting topics, in the next video, we'll explore the universe's anomalies, such as unusual and mysterious celestial objects. To answer these riddles and uncover more secrets of the universe's unknowns, be sure to watch the next video to expand your knowledge of the universe's realities. If you're curious about what the universe is made of and the fabric of space and time, check out the previous video. I hope you found this video intriguing. If you have any feedback, please comment to help improve the content according to your preferences. Don't forget to share this video with your friends and like it. Thanks for watching.